a little bit about the exam today, and then we'll kind of do some review. So once again, those assignments are kind of all due at the end of the day today. After this weekend, I'll hopefully on Sunday have quite a bit of time to grade, so I should be able to get most of the Excel's grade, and then kind of I'll get your grade up there that kind of shows your 4 highest scores, right? Drops the lowest Connect and drops the lowest Excel. That won't show up until I have them all graded. Said I don't know if I'll get it done by Sunday. If not, for sure on Monday sometime. It should pop up where you kind of see what your Connect score is with the lowest drop, what your Excel is with the lowest drop. I've already got up what your iClicker was with those kind of 3 lowest drop. Those will be things that you could use in. Let me see if it's in here. There it is. So that figure out your grade tool that is on the files tab on Canvas, right? So you'll have your first 2 exam scores. You'll then know what your Connect and Excel grade are with the lowest drop, and you kind of already have the iClicker. You kind of plug in your values and then play around with that final exam score to see kind of what do I need to get a certain grade in this class, right? So like here, you know, if I'm trying to get an A, I probably have to get like a pretty good score, right? Maybe 95, whoops, 94, right? And then I might kind of see I'm getting close to that kind of 90 or 90 degree, 90 point level. The exam itself, I can mention this, I think on Wednesday, but it's just going to be 30 multiple choice questions. So, you know, the bulk, you know, the first half of it is going to be 2 population and hypothesis testing stuff, confidence intervals, hypothesis testing. We'll go through some of those examples here in class today, because we hit a little bit harder on Wednesday, the second half of the exam, which will primarily be linear regression, right? So, you know, a lot of the things that we've done, even outside of the practice exams. So once that due date is passed, Saturday, I'll get up the answer keys to both Excels. Although you won't be doing Excel on the exam, you'll notice if you did the 5th Excel assignment, it's a little bit of Excel work and a lot of kind of interpreting the output Excel gives you, right? So a lot of that assignment would be a really good one to use as a study tool as well. So you'll have that answer key, like I said, after tonight. So you can kind of use that as an additional study source as well. Any questions from me before? So I'll bring formula sheet, T tables, and Z tables for that final. You don't have to worry about that. Our exam, I should have had this pulled up or at least memorized. I believe we are Wednesday at 9:45. Let me double check this. Oops. I don't want to get any sections mixed up, but I believe go to the syllabus that's on Canvas. Somewhere down here. And you go all the way to the bottom. He's got, yep, our exam is going to be kind of Wednesday next week, 2-hour time slot, 9:45 to 11:45. If for whatever reason, I think it's something like if you have 3 finals on the same day, you can move one of them. If you know that's your situation, you need to email me as soon as possible so we can get an alternate kind of date set up next week. Like I said, I know that if you have 3 in a week, I think that the university allows you to kind of try to work with one of your professors to move it. But you know, this should be, since it's our time slot, everyone should kind of have this time open during finals week. Like I said, usually we have 20 questions in like less than an hour, so 2 hours for 30 questions should be, I think time shouldn't be a real issue. Other than that, are there any questions about the logistics of the exam before we kind of jump into more like content? Okay. So, for those of you who showed up here today, I'd like to, oops, I didn't do that. Make sure it's worthwhile. So let's go to practice exam A, right? And I think on Monday, we actually worked through kind of how we do these confidence intervals. So kind of had this set up where, look, we've got 3 different types of examples. Difference in sample means, where I've got known population variances, difference in sample means, where I only have sample variances, right, which is what I have here. And then we're looking at the difference in sample proportions. So we said, anytime I see the word proportions, or anytime I know the population variance, that's when I get to use those Z tables. Anytime I only have sample variances, which is also when we're looking at these kind of matched pairs or these mean difference examples, that's where we'll use the student T. So we went to, I pulled up everything except for formula sheet. So if we look at that formula sheet, right? Oops, probably a little bit too much. It's got things kind of grouped in order. So here's kind of our sample means, and we've only got sample variances, right? We talked about last class how we build this confidence interval, right? It's just a matter of plugging in the values that we were given and then finding that t-value that gives us alpha over 2 on each side of the interval. So that's where we kind of left off. The next question was, let's do some hypothesis testing, right? So I end up with this confidence interval, right? And then move on to testing the hypothesis. And here, I didn't ask you to identify one, but that could be a question I ask you on the exam, right? So here, if I wanted you to find the test statistic for this hypothesis test, what's really kind of, how did I come up with that? So we're told here that we want to test for whether or not Indiana has a lower BMI than Ohio, right? So if we're setting this up, okay, what was our group one? Group one was Indiana. So we can think about this as our difference is like Indiana's mean minus Ohio, right? So if what I want to test for is that Indiana has a lower kind of BMI here than Ohio, I mean BMI than Ohio, what am I going to try to assume, or sorry, what am I testing for in my alternative hypothesis? If I want to know, is Indiana's less than Ohio's, what am I saying about that difference? It would have to be, so, yep, so we've got, it would have to be negative, right? If Indiana's is lower, this difference is going to be something that's less than 0. That's what we want to test for, whether or not Indiana has a lower BMI. So we assume the opposite is true, which is that the difference is greater than or equal to 0. So I don't necessarily have to give you, like one of the questions I could add in here is, instead of just directly giving you this null and alternative hypothesis, I could have separated us up into 2 questions. The first one being, suppose you want to test for whether or not Indiana has a lower BMI than Ohio. What is the following kind of null and alternative hypothesis? But whatever you're trying to find, whatever you're trying to test for, so whether or not Indiana has a lower BMI, that is your alternative hypothesis. Now, it might help out to write out what that difference is. And then it kind of, you can kind of see, oh yeah, if Indiana's is smaller, this would have to be less than 0. But the way that we write our null and alternative hypothesis, generally we always kind of use this difference variable, right? So you could have to identify the null and alternative, and this is how you can. Any questions on that idea? What if I had said, I wanted to test for whether or not Indiana and Ohio just had different BMI values? What would my null alternative be?
It was equal.
Yep, so I would be assuming that it's equal to 0, because what I'm trying to find, or what I'm trying to test for, is that difference anything other than 0, right? Are these two means just anything other than each other, right? They're different from each other. Not what we had. So we had this. So what type of tailed test do we have? I look at this alternative hypothesis. I've got a less than, so I've got a left-tailed test. So even before I start calculating things like test statistics, for a left-tailed test, I should be thinking about only evidence on the left-hand side is going to go against the null. My p-value will be kind of the area that's to the left for a left-tailed test of whatever my test statistic is. Now, we haven't calculated the test statistic, right? That would be the next step, which is what question 2 is actually asking, right? What would my test statistic be? Well, I've got my sample means, my sample variances, and my sample sizes up here. If I look at my formula sheet, it reminds me, here's my test statistic equation, right? So these test statistics are just a matter of getting the values plugged in correctly, right? I've got my 2 sample means. I'm going to start kind of plugging these values in, right? 2 sample variances, 2 sample sizes. So if we looked at the original problem, let's see if I can remember all these. So we've got 27 minus 29, right? Those are our 2 sample means. We'll then divide that by the square root of each group's variance over its sample size. So I'll show you what I'm writing down here in just a second. I'm just trying to make sure I get these values correct. All I did was take the values that the problem gave me and I plug them into what that equation was on that formula sheet, right, for our test statistic. Take difference in the sample means. Here, these were our sample variances. Here was our sample sizes. Okay. So one thing to remember is when we're calculating these test statistics, this denominator always represents some standard deviation. So it's always going to be positive. So here, whenever we're using this assumed true difference of 0, which is what I said, like technically, here was the sample difference. We should have subtracted the assumed true difference, but this is always 0. I said I was going to make for you, so we really can just ignore it, right? So that's why I didn't even write it in there, right? So whatever the sign of that sample difference is, if our denominator is always a standard deviation, it's always positive, the sign of our sample difference tells us the sign of our, test statistic. So if I look here, I have 27 minus 29, so -2. So automatically, I can rule out answer A, right? I know it has to be a negative value. Now, from there, it's just a matter of getting these plugged in, right? So unless someone can beat me to it, so this would be what? -2 divided by the square root. So I'm just using Excel to be my calculator. So it's like -1.72 ends up being my test statistic. Okay. Any questions on that one before we keep moving? Okay. So I've got my test statistic, right? Now, this is where on the exam, let's see if I did this here. Probably did. So this is generally how I would try to set these up on the exam too. Just like the last exam with hypothesis testing, you get the first part wrong, and you get cascading errors, right? So on the next one, I say, okay, look, forget what you found in problem 2. Assume that you found this test statistic of -1.55. And I will tell you right now, sometimes it happens to be, in this case, this is kind of close to the real test statistic. Sometimes this assumed true value will be wildly different. So do not read into it at all, right? I sometimes will even change the sign of it just so to kind of make a point, right? But let's assume that we all found the test statistic to be -1.55. So we're all starting off on the same footing. I also told you for these 2 population examples, if you only have sample variances, what would my degrees of freedom be? We had this kind of nasty equation that I said I'm not going to make you use. I'm instead always going to give you this assumed true degrees of freedom. Okay. So in this problem, we want to make our rejection decision, and we want to use kind of the critical value approach, right? So what are my critical values? So I'll also show you how we would find the p-value, but for this one, we're going to look first at critical values. So all the information that I was given, so I have this left-tailed test. I believe I had the 95% level, so my alpha would be what? Yeah, 0.05. Right? My degrees of freedom was 50, right? And I had a left-tailed test. So what I'm thinking about here is my critical value should be the value that gives me the total of alpha in my one tail for a one-tailed test. Okay? So I know the area I want in my tail. I need to work backwards to find this t-value that would be kind of the cutoff number of standard deviations. Now, right away for a left-tailed test, what do I know is going to be true about this critical value? Yeah, remember my z and my t-table are centered around 0, so the left side is always going to be negative values. Right? I'm going to go a certain number of standard deviations below. So the problem is if I go to my student t-table, remember, it always just shows me the right side. Now, that's okay because it's a symmetric distribution. So, for instance, I wanted 0.05 in the left tail. So here's 0.05. That's the area I want in the tail. I go down to my degrees of freedom of 50, 1.676. So the area to the right of positive 1.676 would be the same as the area to the left of that value of a negative, right? It's just a symmetric distribution. So I can get the value from my table, 1.676, but then I have to remember this is a left-tailed test. So it's going to be that number of standard deviations, but going below that assumed true difference of 0. Okay. Any questions on this idea before we keep moving? So if I have a left-tailed test, just to always kind of have this nice visual of the critical value approach, I draw my rejection regions. If for left-tailed test, anything to the left of my critical value. Well, where would my test statistic fall? negative 1.55 was my test statistic that I was given, right? I was told, kind of assume that we found this. I'm not quite inside that rejection region. So here I would fail to reject. Okay. Any questions on that?
So when again, you fail to reject for what reason?
So once I plot my critical value, I can think about the rejection region will be anything more extreme than that. In this case, right to the left.
Okay.
If my test statistic, I plot that against this critical value. If it's not in that range, right, it's not far enough away, it's not a high enough number of standard deviations away where I'm okay rejecting what I assumed or rejecting those. So if it's outside that, I fail to reject them. If, let's say, I had, like the real test statistic was 1.73, well, that one I would have actually rejected the null, right? Because it was past that threshold number of standard deviations away that I was finding for that critical value. Any other questions on that one before I go to the next part? So, right, negative 1.676, and we failed to reject should be the answer for that one. Now, I think I alluded to earlier, what if I instead, let's say I had that assumed true test statistic of negative 1.55, right? And this is where I'll actually kind of mention, so if it wouldn't apply to this specific problem, I'll show you a little bit more of what I would do on the exam. But let's say I gave you this assumed true test statistic, and I instead asked you to find that p-value. So I'm working in the opposite direction where I know my t-value, and I'm trying to find the corresponding area in the tail. Well, the problem is if I look at a degrees of freedom of 50, 1.55 is nowhere in this table, right? So this is where, okay, it's in between these two, so I could say the p-value is somewhere in between 0.1 and 0.05. Now, I won't make you kind of put it in a range. If I ever ask you to find the p-value using the student t-distribution table, I would do something like the following. So let me see. I would say, okay, assume, let's see if I got this number, if I remember it correctly. So 2.043. No, 2.403. So let's say I instead gave you this assumed true test statistic of negative 2.403. And then I asked you to find the p-value, right? The area to the left. So if you go to your table at degrees of freedom of 50, you go over, sure enough, you can find that value of 2.403. So if I ever ask you to find a p-value using the student distribution, I won't make you put it in a range. I'll give you one of these values, right? So here, 403, I go up, maybe. There we go. That corresponds to an area of 0.01. Now, remember, I had a negative 2.403, but once again, it's a symmetric distribution. So the area to the right of positive 2.403, same as the area to the left of negative 2.403, which is what I wanted. So 0.01 in that scenario would end up being my p-value. And then I could make rejection decisions with that. So this is a little bit tricky. It probably won't be this tricky on the exam, but what levels can I reject the null at here in this example? So I found my p-value to be 0.01. So is that less than 0.1? So I can reject that 10% significance level. So less than 0.05. Yep. So I can reject it to 5%. Is it less than 0.01? This is where it's a little tricky. It's not quite less than, right? I don't have less than or equal to. I need it to strictly be less than. So this would be a scenario where I actually would fail to reject at that 1% level. Oh, and you can't see that. There we go. All right. So I might ask you to kind of find a critical value, make the rejection decision. There you're kind of thinking about that rejection region. I could also ask you to find a p-value, make your rejection decision. There it's this rule that we should burn into our minds because it applies to this pre-population hypothesis testing, but also the linear regression when we're trying to decide what we can reject the null for there. This will always be your rejection decision. If that p-value is less than alpha, then you're okay rejecting. Okay. Questions on this before we keep moving here? Okay. So I think that should cover that example and actually give us even more questions than what we're on here. So the next one Let's do this gun ownership one. So we'll deal with some proportions. So let's say instead, we've got assumed, actually, we're doing confidence intervals first. Yeah. Let's say we want to build a 90% confidence interval for the true difference between the proportion of males and females that own guns, right? So, you know, I don't know, there's some survey done. Here's our sample proportions. We had 500 from each group, so pretty high sample sizes. We got our 2 sample proportions, 2 sample sizes. What would my alpha be? 90%, so 0.1. Like, hopefully this is getting to be kind of old hat. We'll go to our formula sheet. We've got proportions. I even use that notation. So hopefully you don't try to use these equations, right? This is, you know, I'm not trying to make it too complicated. I'm keeping the kind of notation the same, right? I'm trying to give you that notation on these practice, also on the exam. We've done those Excel and kind of listing out like what we have. If we've got proportions, we should be using the equations that have P's in them, right? So here's my confidence interval. Here's how I find my test fit. We wanted to build a confidence interval, so this is the equation we'll need to use. We've got everything we need. We just start plugging in our values, right? So 0.37 and 0.31 were our sample proportions. We don't have the Z value yet, but then the second part, well, I'm just plugging in my sample proportions. And I'll show you here in a second. I'm just writing this down to make sure the number is correct. So I'm just plugging in those 2 sample proportions and my 2 sample sizes. Once I plug all those numbers in, I'm gonna have something that looks like this, right? That's all. I mean, at this point, I just have plugged in the information I was given. The only thing left I needed to do was find this Z value, right? Anytime I'm dealing with proportions, I'm dealing with standard normal distribution or the Z tables. So I need to find the Z value that gives me alpha total outside of my interval, which would mean I have half of alpha on each side. We said our alpha was 0.1 before, so the area that I want in the tail is actually 0.05, and each tail should say. So there's 2 ways we could find this. I stopped drawing markers. So the first way maybe makes the most sense. We use the Z table, right? We go down, we find, okay, I know the area in the tail is 0.05, so that's what I've got to find in the middle here. Looks like I'm in between these 2 values, so negative 1.64 and negative 1.65. I'll use the higher of the 2. I have to remember, oh yeah, the positive and negative are kind of like already baked into my lower and upper bound equation. So I just need the value there of 1 point, and I said 645, 65. Right? The reason why I wrote 1.645 is because there's another way that I think if you can remember this, it's easier to find, right? This Z value. So remember we said that T table, the very last row is for my standard normal distribution. So if I wanted 0.05 in my tail, 1.645, right? So 2 ways of finding the same thing. Like I said, I think it's easier to kind of use that last row of the T table, but it's really kind of up to you. Okay. Questions on this before we keep moving? Okay with this? This is, you know, time. Make sure you're asking questions because this is like I don't know. I want people to do well on this final. So, there's something else I was going to say. Now I remember what it was. So if I look at this, right? Can I actually, here I don't think I'm going to be able to, but can I rule out any of these answers? So if I give you some confidence interval options, what has to be true about those confidence intervals? They should be centered around. So before they would be like centered around 1 mean, or they'd be centered around 1 proportion. Now it's going to be centered around the difference I found. So it should be that 0.06 is smack dab in the middle of each one of my confidence intervals. I think in this scenario, it looks like it is, so there's nothing I can really rule out, but I might be a little bit kinder on the exam, giving you like something that only had negative values in it, right? Or something where, you know, it was like 0.05 to 0.1, so 0.06 was not, you know, very visibly not in the middle, right? So maybe you rule 1 or 2 answers out, just knowing like the basic concept of the confidence interval, which is we're basing this range of values around that sample difference we found, okay? So I don't know what this ends up being. We've got the answer key, but we could do this here real quick. So 0.06, oops, minus 2.645 times the square root. See if I can do this without making a typo. If anybody beats me to it, feel free to. Nope, it definitely made a typo somewhere. It was right here. I still have a typo somewhere. Where is it at?
In this parentheses.
0.37 times 1 minus divided by plus. Huh. What am I missing? I don't think this should make a difference, but. Oh, wait, 0.01. Yeah, so I rounded up. It should be, I think it'll end up being C, right? So yeah, and I'll kind of mention this last class, but when we're finding these confidence intervals, like you only have to find one. You find the lower bound there, 0.011, then I know that's the answer, right? If I instead found the upper bound, 0.109, I knew that, right? It doesn't matter. I'm never going to give you like two that have the same upper bound or two that have the same lower bound, right? So it should kind of save you some time. You really only have to find one of those to identify the correct answer. Okay. Any questions on that before we keep moving here? Okay. So I'd like to try to get another hypothesis test in here. So this will be a good one. So let's say I want to do this hypothesis test and I want to find the test statistic. So I might go a little quickly through this because honestly, these test statistic ones, there's only so much I can help you with, right? The real, basic thing you're doing with these test statistics is simply saying, okay, look, I've got this difference in sample proportion example. If I want a test statistic and I go to my formula sheet, here's that test statistic equation, right? It's going to represent a z-value because it's proportion, so it's coming from the standard normal distribution. I'll plug in my two sample proportions, plug in my sample sizes. I have this intermediate step, which is calculating kind of this weighted average between the two proportions. But it's really just a matter of getting our values plugged in, right? 0.37, 0.31, 500 for each. I mean, this is just going to be, making sure you work through more of these examples that you can use your calculator correctly to reproduce the answer. Right? So it's just going to be a matter of plugging our values in here. Okay? Now, one thing we can remember, if I'm doing group 1 minus group 2, so my test statistic, I should have 0.371 minus 0.31. And then I have all that in the denominator, but remember, these always represent standard deviations, right? So I'm taking the sample statistic that I found, dividing it by a standard deviation. Standard deviations are always positive. Whatever sample difference I find, that tells me that the sign of my test statistic. If I find a positive sample difference, that's going to be a certain number of standard deviations above the assumed true difference of 0. So here I automatically know I should have a positive test statistic. So if I'm looking at my possible answers, I'm guessing I can rule out at least one. Right? A doesn't make any sense for me. From here, it's just a matter of getting things plugged in. I guess we could do this real quick. I don't want to waste too much time on it, but let's say we wanted to find P bar. That's just going to be the first sample proportion times that group's sample size plus the next group's sample proportion times that group's sample size. I then need to make sure I'm dividing this by, the sum of those two sample sizes. This is using Excel like I would use my calculator here. So now that I've got P bar, how do I find my test statistic? That's just take that difference in those sample proportions, divide it by square root of P bar times 1 minus P bar. And then that times 1 over each group's sample size. All right, so this is just going to be in making sure you can use your calculator correctly. I'm guessing we get 2.002, all right, or 2.003 if we run. Any questions on that? So we've got that test statistic. Once again, if you got it wrong, you might get the next one wrong. So I give you an assumed true test statistic, right? I said, okay, let's assume that you have this test statistic of 1.45, all right? You've got an alpha of 0.05, and this is the hypothesis test you want to do. So I didn't identify the hypothesis test here, but if I had, what would it, so I've got, is that difference something other than 0? So remember, kind of how I had this set up was the proportion of males gun ownership minus proportion of female gun ownership. So if I had this assumed true, if I was wanting to test for whether or not that difference is something other than 0, what would in words I actually say I'm trying to test for? These are the proportions of gun ownership in males and females. If I want to test for this, is the difference something other than 0? In words, how would I kind of write that out? Or what would that look like?
For the null hypothesis?
So you could do so generally we identify the alternative first because that's what we're trying to find, right? So if I've got this alternative, which is that this difference is something other than 0, what am I really saying about the proportion of male and female gun ownership? I want to test for whether or not they are different, right? So I would say if I want to test for whether or not there's a difference in the proportion of male and female gun ownership, well, then I'm looking for, is there a difference? Is it different than, right? The proportion of male ownership, is it different than the proportion of female? So I'm saying, is that difference something other than 0? So that would be kind of the text I would have if I had been asked to identify the null alternative. I'm trying to test for whether or not there's a difference between the proportion of males and the proportion of female gun ownership, or this could be any example, right? This difference in these proportions. Then I know that I'm saying, okay, what I want to test for is that different something other than 0, which means I assume the opposite is true, which is that it's exactly equal to 0. Right? Once again, I'm always going to use this assumed true difference of 0. So like that should also make it a little bit easier, right? So this different than, we should be thinking about, we've got a not equal to sign. Right? If I want to know, is my first group greater than the other? I have a greater than sign. That difference would be positive. If I want to know, is that first group lower than the other? Well, then my difference would be negative. I'd have a left tail test. So the only 3 types of tests you'll have, right? Left, right, two tail. Okay. So, actually, if I'm being, these are good keywords, right? This is like a good way to approach life, is to look for keywords if you don't know the context of something. So anytime, you want to know, is group 1 greater than group 2? It's a right tail test, right? Anytime you want to know, is group 1 mean or proportion less than group 2? Well, that would make this difference less than 0 or a left tail test, right? So you can kind of think about here, is the difference positive? Here, what you're wanting to test for is the difference negative. And then if you just see this terminology of, are the 2 groups different than each other or different from each other? Well, that's where you've got a two-tailed test and you've got this assumed true difference, right? Where you're trying to test for, is it different than 0? So you're assuming that's exactly equal to 0. So if group 1 is greater than group 2, right-tailed test. Is group 1 have a lower mean or lower proportion than group 2? Left-tailed test. That difference would be negative. Are they different from each other? Two-tailed test, not equal to sign an alternative hypothesis. Okay. Now, I think we were actually given a two-tailed test here. So I've got this test statistic of 1.45. If I want to find the p-value, that's the probability I see my test statistic or anything more extreme. So I've got this test statistic of 1.45. The probability I see that test statistic or anything more extreme, right, or greater in absolute value is this area to the right. However, if I find this area, I'm not quite done, right? So if I got a two-tailed test, what do I need to do once I find this area in one tail? So be careful, right? If it's a two-tailed test, for every value I saw in this range, it would have been equally as likely to see something that went against the null on the other side of the distribution. With our one-tailed test, things on the other side didn't go against the null. They actually supported it. But with a two-tailed test, if we had seen something this many standard deviations below, that would still go against the null. So once we find the area in one tail, that's where we have to multiply it by 2. Okay. Now, I think someone said for subtracting from 1, you might be alluding to or thinking ahead, which is when I look up 1.45 in my Z table, it's going to give me this area to the left. How do I find the area to the right? 1 minus that, and then I'll have to multiply it by 2, right? So if I have a two-tailed test and I have a positive test statistic, probably like the most complicated in the sense that that's where there's the most steps. Because I can look up my test statistic in the table, but the table gives me the area to the left, I need the area to the right. Well, once I have the area in the right, I have to remember, well, it's a two-tailed test, so I need to multiply that area by 2. So what that would look like, we go to our Z tables, we look up 1.45, so 1.45, 0.9265, right? I then have to say, oh, well, I know that's not my p-value, and this is a good check. So let's say I forgot. Like, I forgot to subtract this from 1, right? This is the area to the left, not the area I wanted, which was to the right. If I multiply this by 2, I'm going to get like 1.8 something. Why do I know this can't be the p-value? P-values are probabilities, right? So in fact, only way you can get a p-value of 1 is if you found something that was 0 standard deviations away from what you assumed. So unless you find sample evidence that's exactly what you assumed, you're going to have a p-value less than 1, right? So here, this would be a good indicator I made a mistake. If I draw it out, oh yeah, I wanted the area to the right here. I had to subtract that from 1 to 0.0735, then multiply it by 2. 0.1470 will be kind of my final p-value. Okay. Any questions on that idea? So this would be a good one to point out why it's important you remember to multiply by 2. So let's say I gave you a more open-ended question, and I didn't give you one specific alpha, but I said, at what levels can you reject the null at, right? So if I have a p-value, and I know I can only reject the null if it's less than alpha. So if I have 0.1470, which of the levels, 10, 5, and 1% significance, can I reject that? Well, will my p-value be less than 0.1, 0.05, or 0.01? No, right? So I would actually fail to reject at every single level. Now, what if I had made a mistake, right? And I forgot to multiply this by 2. Or let's just say we had a right-tailed test. How would we approach this? Well, there I would have accidentally seen this p-value of 0.7305, in which case I would actually think I should reject at that 10% level, even though I shouldn't, because I forgot to multiply that p-value by 2. So multiplying that p-value by 2 can sometimes change our rejection decisions as well. But if I have a question where I kind of ask you for a p-value and then kind of leave it open-ended, what levels can you reject at? All you're doing is comparing that p-value to alpha. In fact, I'll probably do a problem like that, where I might just give you an assumed true p-value, like I ask you to find it, and then the next problem I would say, assume that you found the p-value is this. What levels can you reject at, right? That should be, make it even easier if I separate it up into 2 questions like that, which I have the exam written, so I might know how I decided to do it on the actual exam. Okay. There's a couple things I want to mention before we get out of here. We can kind of do some of this. So one set of problems that we didn't work through here, and I will probably work through one of my other sections. So on Wednesday, I posted multiple videos. The first half will be very similar, because we're just kind of covering material from both of my sections. But the second half of those recordings have me going over different practice games. So I've been doing A with you guys, I did B with them, right? So you kind of have me working through more problems if you want to look at those additional videos. One that we didn't work through here today or last class is going to be scenarios where we're given a known population variance. Right? So that's going to be very similar to like the one that we worked through where we had sample variances. The only difference is we use that standard normal as opposed to the t-table. So that's really the only difference, right? And we plug in known population variances instead of sample variances. But once the numbers are plugged in, it really looks no different, right? We're just using a different distribution there. what else? Oh, the other one that we haven't went through, and I'll try to kind of go through a little bit here at the end, are these matched pairs examples. Okay? So these matched pair examples should be even easier than this two population stuff. So this is one where, I don't know, I've got McDonald's and I've got, you know, they made some change, what, posting the calories, probably in the menu, yeah. So let's say I had before and after time periods, right? So it's the same customers, right? The same 42 customers. And I find that this difference variable, right? Take their after consumption of calories minus their before. I then find the mean of that difference variable. I then find the variance of that difference variable, right? And I'm using the notation here, d bar, stamp, you know, s squared, the variance of that difference variable. Hopefully, and the flow of the exam, I'm probably going to be pretty nice. It probably follows the formula sheet, right? So question 1, you probably shouldn't be using stuff from down here. And question 30, you probably shouldn't be using stuff from up here, right? Not trying to play any tricks. So here is where I had these mean difference examples, right? I didn't ask you in this practice exam to do a confidence interval, but if you wanted, you know, if I did, you should be able to, right? You should just be using this equation. We'll look up that t-value the same way that we did for the example earlier where we had sample mean, the difference in sample means and only sample variance. So, you know, here, let's just assume that I wanted to do, I don't know, let's say a 90% confidence level. My alpha value would be what? Yeah, so 0.1. So then when I'm thinking about what I'm doing here, I had that sample difference, and now I already forgot all the values. So what was this? -50. Okay. So I had -50 was my sample difference. My variance was like 22,500, and I had 42 individuals. The only thing left I need to do is find this t-value that gives me alpha total outside of my interval, or alpha over 2 on each side. Right. Now here, I've got this area now, 0.05, and I want in the tail. What's my degrees of freedom? Well, for these matched pairs examples, my degrees of freedom simply goes back to n-1, right? So 42 minus 1 would be what? 41. So I'm going to go up here. Degrees of freedom, 41. The area I want in the tail was 0.05. 1.683. That was the last thing I needed. I can find my upper and lower bound now. Okay. So we can do confidence intervals with matched pairs. I could have also asked you to do what I think the first problem is probably test statistic. So let's say I wanted to find the test statistic for this given null alternative hypothesis. Once again, these test statistic ones, it's just a matter of identifying what the correct formula is and getting comfortable with using your calculator to find this, right? So I've got a matched pair example. I go to my formula sheet. Here's my test statistic, right? Take that sample difference of -50, the variance of 22,500, 42 is my sample size. This shouldn't be too bad, right? This should probably easier than the other ones, right? These matched pairs should be a little bit easier. There's not as many moving parts. Now, right away, I can also remember whatever the sample difference I find is, remember, this denominator represents a standard deviation for this different, like this sample difference variable. So this is always going to be positive. So whatever the sign of my sample difference, that's going to be the sign of my test statistic. With these two population examples, because I'm giving you this assumed true difference of 0, the sign of that numerator in every test statistic equation will tell you the sign of the test statistic. So if I found -50 was that sample difference, I know my test statistic has to be A or C. Okay. Any questions on that before I keep moving here? Try to get through a little bit more before I get out of here. Okay. What if, so I have it in words up here, but just kind of maybe hammer it the point of one. So here I've got what type of cell test. Look at my alternative hypothesis. Left-hand sign, left tail test. So only evidence on the left-hand side should go against the null. I found negative tests. Okay, so I found some evidence on the left-hand side. But how would I kind of say in words what this test is? Well, I'm really looking for, is that mean difference less than 0? Well, how did I calculate that difference? It was after minus before. So I'm really saying there is the average change in calorie consumption negative, right? is that difference something below 0? That's my alternative hypothesis. That's what I'm trying to find. I stacked that against myself, assuming the exact opposite is true. Okay. So I've got this left-tailed test. If I go to the next problem, I have an assumed true test statistic now. So just in case I got the previous one wrong. And I'm asked to find a critical value and make my rejection decision. Right away, which of these answers can I rule out? Yeah, right. If I have a left-tailed test, what I know has to be true about my critical values. Negative. Right-tailed test, critical values have to be positive. Two-tailed test, right? My critical values, and I probably could have done this on the fourth one. I'm going to end up with, for a two-tailed test, it's going to be very similar to what I'm doing with confidence intervals, right? For a two-tailed test, it's going to be, I have a pair of critical values. They now give me alpha over 2 in each tail, right? So finding critical values for a two-tailed test, exactly the same as finding this t-value for how many standard deviations away we need to go when we're building the confidence interval. So right-tailed test, positive critical values, left-tailed test, negative, two-tailed test, 2 critical values, same value, but 1 positive, 1 negative. So left-tailed test, I want, what's the level I wanted? Oh, alpha is 0.05. So I've got a student t distribution, right? Where I know that I've got degrees of freedom of 41. I want 0.05, right, in my tail. This is just a left-tailed test. So 1.683. However, it won't be positive 1.63 because I've got a left-tailed test, right? I wanted the value that gave me my alpha of 0.05 in that lower left tail. So here's my rejection region, right? So negative 1.683. Where would my test statistic be? I think I was told it was what? Negative 2.5. So here I would say I could reject at that level, right? I'm very clearly, my test statistic is more extreme than that critical value, or it's in my rejection region. Questions on that one? I'm running out of time here. So mention, I think what we talked about Wednesday and today, I think it's going to be a really good review. I kind of outlined on Wednesday all the types of questions you should know how to answer for linear regression. I also started out last class, and we're working more examples here today. You kind of see you've got matched pairs, you've got means when you only have sample variances, means when you only have population variances, and difference in sample proportions, right? So all of that's kind of fair game for the final. I'll put an announcement on Canvas, but I will be available most of the day Tuesday. So if there's a time you want to stop by for some last minute studying, feel free to shoot me an email. I can kind of schedule time to make sure like there's not a ton of overlap with people. But feel free to reach out if you have any questions as you're going through things. Other than that, think about you guys about doing the reviews. I saw a lot of you have done it in this section, so I appreciate it. But if you haven't, I really appreciate if you go on and do those faculty evaluations or student evaluations, whatever they call them. Helps me out, helps the college out. Tell you guys, this is actually leaving Ball State after this year. So I'm trying to do learn as much as I can about what I did here to be better for my next position. So I'd really appreciate any kind of comments you leave in there, things you like, things you don't like, just help me get better for the future. Okay? All right. Have a fun, safe weekend, and I will see you guys next Wednesday, right, for the exam.